Greetings, everyone. My name is Justin Skolik, and I'm coming to you on behalf of Team 6. Welcome to our presentation on the ERNIE, or the Enhanced Reconnaissance, Navigation, and Identification Equipment. Our team, which consists of Christopher Schiller, Evan Snyder, and myself, designed this remotely piloted vehicle, or UAS, to assist the National Forest System in search and rescue operations. The objective of our project was to develop a reliable drone-based solution to quickly locate lost hikers. The drone operates in low mountain terrains, performs well in all weather conditions, and is portable for easy deployment. Our design addressed key customer requirements, such as being able to fly below 3,000 feet, sustaining 60-minute flight times, carrying an additional payload of 7.5 pounds, maintaining communication of at least 4,200 meter range to ensure the entire area could be canvassed. We followed an 8-step engineering process, starting with identifying the need, then defining specifications, researching alternatives, and developing designs. After analyzing all the options, we selected the best components, built a prototype, conducted extensive testing, documented our results, and we are now communicating those solutions to you. So we selected the Gannett rotary wing drone powered by an internal combustion engine. It's equipped with EO and IR cameras, LiDAR for terrain mapping, and GPS for navigation. It also has all sorts of sensors and modules contained within its apparatus to monitor its own flight. The ERNIE is designed to meet all of the operational needs. Now, here's an overview of the ERNIE and its component. Our subsystems include internal combustion engine for endurance, manual, and possibly auto-controlled for navigation, multiple cameras for visibility, and to extend the lines of communications, we've fitted it with a dipole antenna. Each choice was validated through rigorous selection process. And for a complete breakdown of the components and specifications, please refer to Appendix A of the written report. The design team identified 14 attributes to consider while the ERNIE was in its development. These attributes were then individually analyzed and tested within the ERAU Hub to ensure their performance matches the National Park Service's requirements. The upcoming slides will outline some of the prototyping tests that verified concept satisfaction, and with a full breakdown of testings and results is available in Appendix B of the written report. Here we can see a concept image of the entire ERNIE system being transported by a standard 1500 series pickup truck. The UAS itself is sitting on a cargo box within the bed of a truck. Now that cargo box can contain extra fuel, replacement parts, emergency equipment, or anything else that the Park Service needs. The truck is pulling a trailer-style ground control unit. Now this ground control unit is also fitted with a large dipole to ensure maximum communication range over the rocky terrain. This setup allows for a small team to transport, deploy, control, and maintain the ERNIE throughout the Yosemite region. The video you're seeing on the screen now was the endurance test that we performed. We sustained flight for over 63 minutes under full crosswinds, and this testing was done with the engine at full power for over 95% of the time. The tester took the ERNIE from 200 all the way up to the flight ceiling max at full bore and back down until the ERNIE ran out of fuel. The ERNIE was fully configured with a suite of sensors and cameras during this test to ensure that its performance will reflect the real-world payload. This video shows the ERNIE's low altitude mobility test. This particular video was taken from 1,500 meters above the ground, yet we tested all of the altitudes listed on the left-hand side of this slide. As you can tell, the ERNIE was responsive and able to exercise pitch, yaw, roll, and throttle. Every altitude of this test was successful. However, at the very low altitudes, the ERNIE ran into a tree, which the simulator did not simulate a crash. So real world testing will need to be done at low altitudes. Here we can demonstrate the ERNIE's mobility, showing its low speed flight that needs to be under 10 nautical miles or 5.1 meters per second, with the ability to hover at 0 for precision scanning. The flight plan on the left is a realistic circular flight plan used to canvass an area to find the lost hiker. On the right-hand side is an in-flight image showing full stability at less than 1 meter per second of ground speed. This video is to demonstrate the functionality of the ERNIE's camera systems and control. The cameras are all placed on a gimbal that sits below the chassis itself. And in this video, you can see that the gimbal was fully able to articulate 90 degrees vertically and then pan a 360 horizontal. At the end of the video, there is an 8 times zoom function that is demonstrated. This test was fully satisfactory. The images on this slide show the effectiveness of the cameras aboard the ERNIE. The leftmost camera is the RGB image taken in low visibility environments. In the simulator, we used 100% fog. The middle image is the same camera, but with 0% fog on a clear day, and you can begin to make the outline of the wolf. On the rightmost is the IR in full fog. As you can see, the FLIR camera detects the heat signatures in low visibility. Then we can switch to the RGB camera to provide visual confirmation. The visibility comparison shows the effectiveness in all environmental conditions. Here we can see the LiDAR sensor enabled on the ERNIE to navigate complex terrains by mapping changes to the various intervals. This ensures a safe flight path through Yosemite's rugged environment. Our communication test demonstrated a range up to 4,200 meters with additional antennas. This flight plan shows Team 6 tested the communication range of the ERNIE using a straight line flight path. Now, because of the rocky terrains, we were unable to get the full 4,200 meters with simply the dipole on the ERNIE and the dipole on the ground control station. However, if we were to place extra antennas on top of some of the mountainous regions throughout the flight arena, we were able to maintain full communication corner to corner of the map. So in summary, the ERNIE has met or exceeded all of the key performance metrics, including endurance, altitude, communication range, and payload capacity. You please refer to the testing matrix in Appendix B of the written report to see the specifics of each individual test. But there were some limitations. Our design performed well in the simulation, but limitations for auto landing and noise testing couldn't be fully evaluated. Real-world testing is going to be necessary before we can field a successful drone to help the National Park Services with their search and rescue efforts. So there you have the ERNIE. It can be a very valuable tool that you can load onto a truck and deploy to help some tourists who maybe got off the beaten path find the hero that they're looking for. We really appreciate your consideration, and we'll be staying back for any additional questions or specifications that we did not cover that you might be interested in. Thank you for your time.